Hi, welcome to AB Video 3.9b Part 1, more on differentials, and an introduction to what's called the tangent line approximation, or what's also called the linear approximation. Okay, so these are two sets of questions in 3.9 on differentials. It says use differentials. In this case, they're giving you the graph of f. Now, in the next one, they're going to give you f prime, and in this case, they give you the graph of f. They're asking you to approximate, which is what differentials are all about. It's an approximation in the change in y as opposed to the actual change in y. And they want you to approximate f of 1.9 and f of 2.04. Both numbers, of course, are very close to 2, which is exactly the point of tangency. Okay, so if we use our formula, we know that I'm going to go right down here. So I'm going to do it using differentials. So f of 1.9 is obviously f of 2. Okay, so at 1.9 would be about here. So f of 1.9 would be up here on the actual black f graph. But it is equal to f of 2 plus the change in y. So we're here at a height of 1. So obviously, we have a change in height when we get to 1.9 comma whatever it is on the black graph. So there's an actual change in height right here. Okay, so that's the actual change in height. But we know that the actual change in height is approximately equal to dy, the differential of y. So because we know dy is approximately the same thing as delta y. Now, what is dx? If you remember on the right here, dx is actually, dy you find by finding dy dx and then sending the dx to the other side, okay? And the 2, of course, is because that's the number it's closest to, plus it's the only number we have. Okay, so f of 2, as you can see, is 1, and then I'm going to go over here on the right to show you how I get that 0.1, okay, for dy. So dy is f prime of x dx. So dy is f prime of 2, which is our pretty number. And dx is the change in x. Now, it's always going to be the ugly number first, the approximate number, sorry, not approximate number, the decimal number, minus the pretty number, that being the x-coordinate of the point of tangency. So it's f prime of 2 times 1.9 minus 2. So we have to figure out f prime of x. Oh, I don't have the function, so can't figure out what f prime of x is algebraically, but I absolutely can figure out what f prime of 2 is equal to, because f prime of 2 is the slope of the tangent line to the graph of f at 2. So all we have to do is figure out the slope of this line. And of course we can do that the old algebra 1 way, which is rise over run. So you can see that if I take this point 2, 1, and they purposely make sure that you know a specific other point, which is the point 3, 0. So if I find the slope between them, which is right here, so the slope of the tangent line at 2, 1 is the slope between those 2 points, 2, 1 and 3, 0, and all I do is y2 minus y1 over x2 minus x1, I will get negative 1. So f prime of 2 is negative 1. The ugly number 1.9 minus the pretty number 2 is negative 0.1, and that's obvious on the graph that to get to 1.9 comma something, we're moving to the left. So it makes sense that the delta x is negative. Okay, so we multiply that together. We find out that dy is 0.1. We take that dy, plug it in here, and our approximation is 1.1. You do the exact same thing for f to approximate f of 2.4. F of 2.4 would be exactly equal to f of 2 plus delta y, but delta y is approximately equal to dy. Again, over on the side, dy is f prime of x dx. Our pretty number x is 2, and this is ugly minus pretty, which is 2.04 minus 2. This time we get a positive here, but then we are multiplying it by negative 1, so we get a negative 0.04. Why does that not make sense? But apparently it does. Okay. Oh, because it's the dy, and we are dropping, right? If you go back to the graph, as we move to the right to get to 2.04, the heights are actually dropping, so the delta y is actually negative. Whereas here the dy was 0.1, and that's because we were moving to the left and therefore had to move up, and that's why the delta y was positive. Okay, so we take that negative 0.04, plug it in here, subtract, and we get an approximation. All right, this is a bit different. You have been given this time the graph of G prime, not G, and they're asking you to approximate G of 2.93 and also approximate G of 3.1. So both of these numbers, of course, are very close to 3, which is right here. Now remember, this is not G of 3, this is G prime of 3, which is why they have to give you the value of G of 3 up here, otherwise you'd have no way of knowing what it is. So that pretty number is 3. Well, our first ugly number is 2.93. Again, that would be G of 3 plus delta y, but replace delta y by approximately dy. G of 3 they gave us is 8. We have to figure out delta y. Dy. So dy dx is g prime of x dx, which means dy is g prime of x equals g prime of x dx. You have dy equals, therefore, g prime of 3, the pretty number 3. Remember, it's always ugly minus pretty, or decimal minus integer. So 2.93 minus 2, and that gives you a value of dy of negative 0.21. So I come back over here, plug it in, and we're done. Same thing exactly for the other one, only it's 3.1 minus 3. So that gives a dy of 0.3. Okay, totally last topic in Chapter 3, tangent line approximation. Okay, looking at this graph, I have a blue graph here, f of x. I have a point on that blue graph, 2, f of 2. Now, so my x is 2. So I'm going to go a little bit to the right. Now, obviously, I've gone way further to the right than I should, but if I made it too close, you wouldn't be able to see what's happening that close. But the idea is that it is very close. And the first thing I want you to notice right here is right near that point of tangency, the blue curved graph and the red tangent line, the y values and the x values for that matter, the points are almost touching each other, okay? Obviously, the further away I move from that point of tangency, the further and further away the y values of the blue and the red start to separate, and they become very different, okay? But right near 2, okay? All right, so let's say I want to approximate f of 2.01. I'd like to know what the approximate value of that is. The exact value would mean that I have to plug 2.01 into f of x, and that's what we're trying to avoid, is having to deal with the decimals by hand. So what we're going to do is, instead of evaluating f of 2.01, we're going to evaluate g, which is g of x being the tangent line, g of 2.01, because the heights of these 2 points are very close. And of course, 2.01 is actually here, and you can't even tell the difference between the heights. It's minuscule, and that's why it's a good approximation. Okay, so g of x is the tangent line to f of x at the point 2, f of 2. Therefore, y2 minus y1 equals m times x2 minus x1. Y minus y1 equals m times x minus x1. Our y1 is the y coordinate of the point of tangency, which is f of 2, and our x1 is our 2. The slope, of course, would be f prime of 2, because that's the slope of the tangent line to f of x at the point 2, f of 2. Therefore, if I isolate y, I get y equals f of 2 plus f prime of 2 times x minus 2. Well, y, of course, what is this function? This function is our g of x function, right? This is the equation. I just found the equation of the tangent line, which I'm calling g of x. Now, when you look at the graph, and we just talked about this, f of 2.01 is very close to g of 2.01. The heights of these 2 points are very, very close to each other. But what is g of 2.01? G of 2.01 is f of 2 plus f prime of 2, and let me fix this, and that's 2.01. Right, because I'm evaluating g of 2.01, so I'll replace the x here by 2.01. If you were to let, I'm going to get a general formula. I did it for the point where x equals 2, but if you did a general formula, if you let x0, the pretty number, the point of tangency, x coordinate be the 2, and you let x be the 2.1, which is the uglier number very close to 2. In other words, my delta x here, or my dx, which are the same, are the difference between these, and I am moving to the right, so it makes sense that it's positive. So if I take this formula up here and I replace the 2.01 by x, I replace the two 2.01s by x, and I replace all the 2's by x0, okay, x0 and x0, this is the tangent line approximation formula. So, if you're looking for f being the original function at an ugly number x, it will be approximately equal to f of the pretty number x0, the x-coordinate of that point of tangency basically, plus the slope there, which is f prime of x0, times the ugly number, that's the decimal, minus the pretty number that it's close to. Okay, so obviously, though, for a really good approximation, delta x is going to have to be very small. We talked about that. If delta x is too big, if you're all the way over here, then the heights of the two graphs are very, very different. But the closer and closer and closer you are to the point of tangency, the more the heights of the points are all extremely close to one another. So in conclusion, we can approximate the value of f of x, where x is close to x0, by finding the y value for that x value on the tangent line to f of x at x0, f of x0. And that's the end of video 3.9b, part 1.